This section is all about diagonalization, which we touched on briefly in the last section. This diagonalization theorem just says that if you have an n by n, so a square matrix, then it is diagonalizable if and only if it has n linearly independent eigenvectors. When you form the factorization, the PDP inverse, the matrix D, the diagonal matrix, has the eigenvalues on it, and the matrix P is made up of the corresponding eigenvectors. So in this first exercise, you are given this factorization of, you have PD, P inverse, and we want to use the theorem to identify the eigenvalues of A and a basis for each eigenspace. So we have lambda equals 5 because of this, and we have lambda equals 1, and notice that's a double root. The matrix P is made up of the eigenvectors corresponding to these eigenvalues. So because my 5 is first, this 1, 1, 1 is a basis for the eigenspace corresponding to lambda equals 5. A basis for the eigenspace for lambda equals 1 is going to be the other 2, again because it's a double root. Exercise 2 says that this matrix factorization is not unique. So given this factorization, again we have P, D, P inverse, I'm going to write an alternative form. So I could also say that A is equal to, I can swap the order of my eigenvectors, which swaps the order of my eigenvalues. And then I can't just swap the order of the P inverse. I actually have to find the inverse of my new P. So here is an alternative factorization for A. You can always check your answer by multiplying them out and seeing that you actually do get that original matrix A. Theorem 6 tells us that a square matrix with n distinct eigenvalues is diagonalizable. So n distinct eigenvalues, distinct just means there are no repeated ones. In order to find the PDP inverse, we go through this process. You're going to first find the eigenvalues. That'll tell you what goes on the diagonal matrix. Then you'll find the eigenvectors, which tells you what goes in the P's. Then you can find P inverse using whatever method you want. Then construct the PDP inverse, making sure that the order of your eigenvalues is the same as the order of the eigenvectors. Exercise 3 gives us a matrix, and it tells us the eigenvalues and asks, is it diagonalizable? And we say yes, we know that immediately. Because it's a 2 by 2, there will be 2 eigenvalues. Because they are different, that means they are distinct, so it is guaranteed to be diagonalizable. In order to find the matrix P, I'm going to find the eigenvectors that correspond to that. So eigenvectors are from doing A minus lambda I x equals 0. So for lambda equals 5, I'm going to subtract 5 off my diagonal, augment with zeros. x2 is free, and then x1 is equal to x2. So in vector form, x2, x2, or you can just write 1, 1, or 2, 2, or anything that has the same. For lambda equals -2, I'm going to add 2 on the diagonal entries, row reduce. So x2 is free, and I know that 4x1 plus 3x2 equals 0. Solving for x1, I get -3/4 x2. So in vector form, I have x2 is free. My x1 is -3/4 x2. I'm going to choose x2 to be 4 so that I get a -3. So if I want to create my P, I'd have 1, 1, -3, 4. My D would be 5, 0, 0, -2. And then in order to find the P inverse, I need to find the inverse of my P. So this inverse is equal to, so here is my factorization. I just want to point out that I found P, D, and P inverse, but really it says find the vertical matrix P and the diagonal matrix D such that this is true. So it doesn't actually ask you to find it. So if you want to check your answer, so we have that A equals P, D, P inverse. If we multiply on the right by P, this P and P inverse is the identity, so that tells me that AP equals PD. So you could check that instead of finding P inverse, so just a different note. So we can use this diagonalization to help us compute powers of a matrix. When you compute A to like the 100th power, if you actually had a 100 by 100 matrix raising it to the 100th power, that would be very, very computationally intensive. So instead, what we can do is use this fact that A to the K equals P times D to the K, P inverse. And the reason why this is a shortcut is because D to the K is just the entries all to the kth power. So let's use A's factorization, again this P, D, P inverse, to compute A to the 5th. So A to the 5th is P D to the 5th power times P inverse. And when you're raising a diagonal matrix to the 5th power, you raise each of the diagonal elements. So 2 to the 5th is 32, 1 to the 5th is 1. And then we can multiply out. I multiplied these first two, and now I'm going to multiply by that third matrix. And I get -92, 372, -31, and 125. So that's a whole lot easier than multiplying A times itself 5 times. And really where this comes in handy is when you're trying to raise to a very large power. So 5 is not that large, but if you wanted to do to the 100, the 1,000. So while this is not going to be on the exam, I thought I'd at least touch on diagonalizable matrices whose eigenvalues are not distinct. So the key here is that in order to be diagonalizable, you have to have the right number of independent eigenvectors. So we know we have independent eigenvectors if we have distinct eigenvalues. But like in this exercise, notice because it's triangular, you can see that the eigenvalues are 5 and 5. So I can't just tell because the 5 is repeated that it's not diagonalizable. I'm going to find the eigenspace corresponding to lambda equals 5. So again, I want to think about A minus lambda I, x equals 0. So subtract 5 off the diagonals, I get 0, 1, 0, 0. This tells me that x2 is 0 and x1 is free. So the basis would look like this, or you might say 1, 0. Because there's only one vector in my basis for the eigenspace, but 5 is repeated twice, that tells me this is not diagonalizable. So in other words, this would need to have 2 vectors. So in exercise 6, we are given A, and we're asked to diagonalize it if possible. So because I have a repeated root of 1, I want to look at the eigenspace corresponding to lambda equals 1. So again, a minus lambda I, x equals 0. So here my lambda is 1. I'm going to subtract 1 off the diagonal and row reduce. Notice that I have 2 free variables, so x3 is free, x2 is free, and the first line says that x1 plus 2x2 minus x3 equals 0. So x1 is equal to negative 2x2 plus x3. So generic form, x3 is free, x2 is free, and I have negative 2x2 plus x3. Because there are 2 free variables, I will have 2 basis elements corresponding to lambda equals 1. So if I break this down into some vector times x2 plus some vector times x3, the coefficients of the x2 are negative 2, 1, and 0, and this is 1, 0, 1. So I have 2 elements, these 2 elements, in the basis for the eigenspace corresponding to lambda equals 1. So there'll be 2 columns in my matrix P. So because lambda equals 1 works, I'm now going to find the an eigenvector corresponding to lambda equals 5. Here's my row reduced matrix. I have that x3 is free, x2 equals negative x3, and x1 equals negative x3. So an eigenvector corresponding to lambda equals 5 would be 1, negative 1, negative 1, going up. So my P would be negative 2, 1, 0, 1, 0, 1, negative 1, negative 1, 1. And my D, again, I have to write the eigenvalues in the right order. I put 1s first, and then the 5. So it is diagonalizable, and there's my P and my D that make it diagonalizable.